So our final speaker now, speaking about heat pumps, technology recently described by Dr. Benjamin Crick of the Passive House Institute as the heating system of the future. We have Vincent Mahony from Panasonic. He's the National Account Manager with Panasonic Ireland. He's over 34 years experience in the building service industry, mainly in air conditioning. He served his time as an AC engineer with Walker Air Conditioning, thereafter working in design and sales in Northern Ireland and the UK. And he worked next as sales director of Walker Air Limited and joined Sanyo Air Conditioning in 2006 and 2011, and is currently general manager of Panasonic Heating and Cooling Systems Ireland, responsible for sales in the 32 counties. Thanks.
Thank you. I will also be asking Tony Duffy, my colleague, to come up and talk about a few of the more difficult slides. So, air-to-water technology. Looking at a quick overview of the agenda, just looking at how much energy we use in the home, then looking at the fundamentals of air-to-water heat pumps and their applications, test criteria for air-to-water heat pumps, and then we'll be taking a look at comparison between different types of heat pumps. Then looking to see what we actually need, the information we need to select a unit, looking at some examples, and just finishing up with some pros and cons of each. So how much energy do we use in the home traditionally? So today, for heating and hot water, we can use up to 74%. That better? 74% of the energy we use in the home goes towards hot water and heating. Fair amount of heating. And that is traditionally down to poor insulation, infiltration, and inefficient heating systems. Now, the houses that are built today, of course, are a lot more efficient, and infiltration is reduced, and the insulating materials, etc., are a lot better. But we also look at the heating systems that go into those houses, because the energy that we pay is extremely expensive. Electricity prices from 2000 to 2013 are in the light green there in the middle. Oil prices, again the light green in the middle, significant increases since 2000. And natural gas, a lot more spikes, but it hasn't increased as some of the others. So looking at that across all three, this is for Europe using 2005 as a base point. We see that for Ireland, electricity costs have increased by 17%, oil by 38%, and natural gas by 28%. So what are we looking for a heating system? We're looking at a unit that can provide hot water and heating, of course, whether that's to an underfloor heating system or to traditional RADs or to low temperature radiators. Environmentally friendly solution. Ideally, if we can utilise free energy from a renewable source, it has to, of course, have suitable flow temperatures, whether that's to a radiator system or to underfloor. Efficient, leading to low running costs and low carbon emissions, and of course proven technology, easy to install and minimal maintenance. Maybe air-to-water heat pumps is a solution to that. So what is an air-to-water heat pump? Well, it's really a refrigerator in reverse. We've got four fundamental parts. We have a compressor, a condenser, an expansion device, and an evaporator. And essentially what we're doing is, in that system, that's a closed circuit, which we don't need to get involved in. We have a heat exchanger here, and then we have hot water going into the house. Ideally suited to wherever you need hot water and heating. New builds, old buildings, anywhere where you're looking to improve the PEO rating. In air-to-water units, there's two types of construction. There's what we call a bi-block, where we have, can we see that? An outdoor unit and an indoor unit. And between both, we have direct expansion or refrigeration pipework. And then we have our plumber's copper going around the system. There's new units also which have a combined cylinder and hot water tank. Then there's monoblock units which comprise the indoor and the outdoor unit all together. It all sits at the outdoor unit, so the pipework going into the building is through plumber's copper only. So where would we use monoblock units? Or the advantages of using monoblock is there's no refrigeration pipework required. So you don't have to worry about any F-gas regulations. It can be installed by any reputable installer. But because we've got water in the outside system, you may need to look at adding glycol. You also need to look at the distances between the outdoor unit and the indoor unit, because you may have losses in thermal capacity. So you need to make sure that the insulation that you utilise is of a high standard. With bi-block or split systems, we have the outdoor unit, we have the indoor unit, and we have refrigeration pipework in between the two. So essentially, they can be piped up to 30 metres away. You have no need to add glycol to the system, and you're guaranteed your flow temperatures. We have heating only units, or heating and cooling. Not so much the Irish marketplace for heating and cooling, certainly in domestic applications, but it's available. There's 3 types of units which Panasonic manufacture. There's the standard high efficiency type with COPs up to 5.08, which I'll talk about COPs in a moment. Capacity range from 3 to 16 kilowatts with a max flow temperature of 55 degrees C. There's total capacity units which can guarantee heat outputs down to ambience of minus 15 degrees C. Capacity range 9 to 16 kilowatts. Again, high COPs, not quite as good as some of the standard units. And again, a max flow temperature up to 55. And then we have high temperature units. There's water flow up to 65, but that's only available in 9 and 12 kilowatts. For heating, we can guarantee heat output down to ambience of minus 20 degrees C. But if we're utilising the heating and cooling units as well, we will only get cooling down to ambience of plus 16 degrees C. So it is only for comfort cooling. So when we talk about air-to-water heat pumps, we hear the term COP or coefficient of performance quite a lot. What exactly is that? It's simply the heat output divided by the power input. So if we have a heat output from a heat pump unit of 5 kilowatts and a power input of 1 kilowatt into the compressor, we have a COP of 5. So we're taking 4 kilowatts from the air around the unit. So although that air may be cold, there's still energy and still heat in that air, which we can utilise to heating the home. A COP will decrease as water temperature increases and outdoor temperature decreases. In the test conditions for heat pumps, when we hear a unit has a capacity of 12 kilowatts or 9 kilowatts, etc., it is at air at 7, water at 35. But when we're looking at the DIP software, we don't just look at COP at air at 7, water at 35. We look at the SPF, which is the seasonal performance factor, which is based more so on Irish conditions. So it's across the heating season. And those temperatures are at air at 7, water at 45, air at 7, water at 35, and air at 2, water at 35. So, just going to go on to a document here for 1 moment. So heat pumps have to be tested by an independent testing agency. So this is one of Panasonic's units. It's a TCAP 9 kilowatt unit. It was tested by IGE in Germany. And they have to independently test these units. They don't just take Panasonic's good word. And this is the document that we have to give to SEAI for them to put on the hard database. So it gives a brief description of the unit. It shows photographs not only of the unit but the nameplates and certain elements of the unit. It details the heat exchangers, the compressors, etc. So for this unit, we have it rated at, I don't know if you can see there towards the bottom, 4.74. So that's a COP 4.74. So for every kilowatt we're putting in, every kilowatt of energy we're putting into the unit, we're getting 4.74 kilowatts of heat out. So the test criteria that they tested to are to all these different conditions here. Because for all over Europe they'll have different testing criteria. So for air at 7, water at 35, which we had 4.74, it actually came out 4.89, slightly better. But when we look at the three conditions that we have to test it to for HARP, which is air at 7, water at 35, air at 2, water at 35, and air at 7 and 35, we get an average figure of 4.107. So that's the figure that the PER assessor then uses. And that's what he sees then on the HARP database. So it gives the information about the unit, when it was manufactured, the SPF, the seasonal performance factor, and then contact details for the manufacturer. Now going forward, those test criteria will change. EN 14511 will change. There'll be two test criteria, EN 14825 for space heating and 16147 for water heating. They will probably come into effect from late 2015, 2016. So as I say, the efficiency of the COP will drop as ambient drops. You see the first bar is tested at air at 7, water at 35. In the second bar you see the COP has dropped from 4.85 to 3.07 for water at 55. And that's listed in all manufacturers' literature. So COP at plus 7, water 35, 4.74, but then at minus 7, it's 2.81. And even when we go to higher temperatures, for example, water up to 55 degrees C, the COPs will still be reasonable. So I spoke earlier about three different types of units: the standard high connectivity type, the total capacity type, and high temperature. So the units I tested, I don't know how well you can see that, but here's the ambient temperature down here, going from plus 25 to minus 15. Here's the heat output going from 4.5 up to 9.5, and here's different water temperatures. So the unit is tested at air at 7 and water at 35. So this is a standard 9 kilowatt unit. But see what happens once the ambient drops below 9 degrees C. It doesn't just decrease, it plummets. And that's one of the issues that we've had in the past with air-to-water heat pumps, is that they weren't correctly designed for the application. It's fine at air at 7, you're getting a duty, but when the air drops to 0 or minus 5 or minus 10, we have considerable issues. So you have to size it for the proper ambient temperature. But if we look at a total capacity unit or a TCAP unit, it's flat line. So no matter what the ambient, down to minus 15, we're still getting our 9 kilowatts thermal capacity. And in fact, if we go above 7 degrees C, we're actually getting a lot more. Whereas if you look at a standard unit, it actually decreases a little bit as the temperature rises. So you have to be certain in the design stage about what unit you want to go for. 12 kilowatt unit, standard, not quite as bad as the 9 kilowatt. And the 12 kilowatt TCAP unit, not quite as good as the 9 kilowatt TCAP. But that thermal drop off is only at higher water temperatures, and it's when the ambient gets to about -8 degrees C. High temperature units also have TCAP technology. So with standard units, in red, we have a definite thermal drop off, but for high temperature and TCAP, we don't. With water at 35, we do at slightly higher water temperatures. So that's a 9 kilowatt high temperature unit. So at water at 35, we're maintaining that 9 kilowatts. And with the 12 kilowatt high temperature unit, again water at 35, we're maintaining that. But you will have a thermal drop off at high water temperatures. But of course, one of the advantages with high temperature units is they can heat to 65 degrees C, and that will have an effect on your BER rating. Because your BER assessor can take a look at the possible supply water temperature from the high temperature unit and give it a factor of 1 for water heating. Whereas for units that supply water below 60 degrees C, he has to take a figure of 0.5. So design. So if we're looking at the thermal load of a building, to do it correctly, we should really be engaging an engineer to look at all of the heat loads for each of the rooms and the space. We need to take a look at the location and the many occupants and the type of heating system that you're putting in there. So as I say, you engage an engineer to take a look at the heat load for your building. But these are rough figures, extremely rough, only as a guide, only as a rule of thumb only. So for passive houses, we're probably talking about 10 watts a square metre. For my house, built in 95, a bit more. So if we're looking, let's say, for example, at a 110 square metre house built in 1980, we're talking about 100 watts a square metre, as a rule of thumb, roughly, so about 11 kilowatts. We then need to look at the location. This is a pretty good website, fundaground.com. It has ambient conditions for all of the major European cities. This is for Dublin between the 1st of October 2010 to the 31st of March 2011, which was one of the bad winters that we had. So the warmest day that we had during that 6-month spell, the max temperature got to 19 and the minimum on that warmest day was 13. It was the coldest day, the max temperature reached -5 and it got down to -11. So what do we design to? Do we design to -11? Probably not, because we're probably going to be oversizing our units. But certainly we should be looking at maybe around -5. So looking at a unit then to heat that 11 kilowatts heating capacity. A standard 12 kilowatt unit, which you would think would perhaps be able to do a 11 kilowatt load, but a standard unit with water at 50 degrees C, we're only getting 9 kilowatts. So therefore, every time the ambient drops below 4.5 degrees C, we're utilising electric heaters, which is going to have a significant effect on the end user's bills. Whereas a 12 kilowatt TCAP unit will give you 12 kilowatts all the way. It's only when it gets to about -8 that you do have a small bit of drop off. So these are standard units. So we could probably get away, for that -5, we could probably get away with a nominal 14 kilowatt unit. And remember that 14 kilowatt is at air at 7, water at 35. But we may need to look at a 16 kilowatt unit. So that's a standard heat pump. Whereas if we look at a total capacity unit, we get away with the 12 kilowatt all the way down. Hot water requirements. Normally we're talking about 50 litres hot water a person a day. Unless you have teenage daughters where it can be considerably greater. So generally when we're looking to size the cylinder, we take a look at the number of bedrooms, add one and multiply by 45 litres. Because of course our heat pump is heating not just the RAS, but of course the hot water. Now there's software that we have on PanasonicProClub.com that has weather data already built in, that you can either put in the size of the building when it was built, etc., or you can put in your thermal load if it's been calculated by an engineer. And what that will do is that will select a unit for you, whether it's a standard, whether it's high temperature, or whether it's TCAP. You can select which unit you want to go for, or the quantity of units. And it gives you a report. And that report will give you the heating and hot water load for the year. It will give you an average COP for the full year. So it's not just looking at the design condition of -5 or a +2. It's looking at it for the whole year for wherever your unit is located. And then it gives you estimated annual running costs plus your carbon emissions. And then that compares that to other forms of heating. So how is the system piped in? Tony, can you take this?
This is a monoblock system. Sorry, I'm used to shouting in a room. This is a monoblock system. Basically, the monoblock outdoor unit is positioned outside of the property. You've got a flow and return pipework. Flow and return pipework coming into the house. Okay, friends. We size the heat pump for the biggest load, be it the heating in the house or the hot water. In a passive house, the biggest load is probably going to be your hot water demand. Okay, but the heat pump is sized to do your biggest load, one or the other. It's not sized for both. So we have a flow and return coming into the house. We're feeding the domestic hot water cylinder first. So when we commission the heat pump first thing we do is we charge the hot water cylinder. Once the hot water demand is satisfied, then there's a sensor in here. It switches the heat pump into the heating mode, which switches the three-way valve and diverts the water flow into the heating circuit. Heating circuit can be underfloor, can be low temperature radiators, can be standard radiators, can be fan coils. It's just a heat emitter. Okay, you decide, the engineer decides, the architect decides, the customer decides what his heat emitter is. The set point for the heating side depends on your heating emitter. If you have low temperature radiators, you can have 45 degrees. Standard radiators can be 55 to 65 degrees, on the floor 35. It just does depend on the heating emitter. There are two set points programmed into the heat pump, one for the domestic hot water, one for the heat pump, or one for the heating cycle, excuse me. In the cycles which are programmed when you commission the system, you decide what your set point in your tank is, what your set point in your heating system is. Weather compensation is built in on the heating side, not on the domestic hot water side. The domestic hot water temperature has to be constant. So weather compensation is built in on the heating side, so depending on the ambient temperature, you can shift the design flow temperature, the calculated flow temperature, to your heating system. So as your temperature externally rises, your flow temperature to your heating system decreases. Okay, and that's basically just a schematic of that. Up here then we have our control connections. Okay, and basically everything is wired back. These control connections are actually inside the heat pump, and everything is wired back to the heat pump. Alright, the heat pump controller does everything itself, it does everything for you. You can connect the heat pump controller to, or the heat pump unit to a standard domestic time clock, to a simple, very simple control system that the end user can use, that you don't want him interfering with the heat pump controller. Okay, but again, if a guy is technically savvy, there's no problem at all for him to interfere with the heat pump controller. Nothing you do to the heat pump controller will damage the heat pump. Okay, unless you hit it with a hammer, of course, but nothing you do to the heat pump controller by pressing buttons will damage the heat pump. If you change settings, obviously it's going to change how efficient the system operates, but in order to change how the system is programmed, you have to press a certain few buttons on the controller in a specific sequence, which gives you access to the setting code. So it's not a simple thing to do, you know. On a split system, this is a monoblock system which is more popular. Okay, the monoblock is positioned outside the house. You've got flow and return water pipes going into the property. As Vincent explained earlier, the fact that you have water leaving the property, then you have to worry about your frost protection. Frost protection is built into the system, but it's electric.
Okay, so it does protect itself with frost, but it is electric. If you lose power, you have no frost protection. Okay, so then in a situation like that, it's advisable to introduce glycol or some kind of antifreeze to the system. With a split system, the heat exchanger is located inside the house. And again, the heating side and the domestic hot water is exactly the same. There's no difference, okay? The only difference is you have refrigerant pipework onto the outdoor unit. Okay, this does then come under the whole F-gas regulation that a certified F-gas engineer has to do the final connections, has to pressure test the system, has to evacuate the system, and then has to open the valves. There should be no need for the engineer to add a refrigerant to the system. The system is charged with up to 30 meters, for up to 30 meters of pipework. If you want to go further, yeah, there is a requirement to add refrigerant, but it's bread and butter for any refrigeration guy. It's not a complicated process whatsoever. Okay? All split systems have less than 3 kilograms of refrigerant in them, so they don't come under the F-gas regulation. They do not need to be leak tested once a year, as the F-gas regulations stand at present. Okay, if that changes, obviously, things will change. Okay, and the advantage of a split system, as Vincent mentioned earlier, is you don't have to worry about frost protection. The water isn't leaving the house. Okay, so technically speaking, there's no requirement for glycol. All right. We can also connect to a bivalent system. What have we got here? We can also connect bivalent. We can connect to a system that has an existing oil or gas boiler. Sometimes we're told that a client has an existing oil or gas boiler and they don't want to remove the boiler. Okay, it's fine. Based on the electrical supply to the house, they might not be able to. They might need 2 heat pumps for the house. In a very large house, for instance, they may need 2 heat pumps. The electrical supply to the house might not allow them to run 2 heat pumps. They install 1 heat pump. They install a bivalent. They keep their existing boiler. We have a product which we call a heat pump manager, which will control the switching between the heat pump and the boiler. We can have true bivalent at a certain temperature. The heat pump shuts off, the boiler takes over, or we can have cascade, whereas the heat pump will always run and the boiler will come in periodically to back up the flow temperatures. This is controlled from a heat pump manager. As Scott explained earlier, intelligent PV control now is becoming much more prevalent in all appliances, integrating with PV. The heat pump manager can also look at the energy that's been produced by a PV system, and it can, you program certain limits into it, etc. If there's a certain amount of kilowatts coming from your PV system, you can then, while you're out of the house, you can switch on your heat pump, and you can charge a heating system with a certain amount of water. If you have a large buffer vessel, if you have large storage for domestic hot water or for heating, you can heat the thermal store to a level which is far above your calculated set point. Okay, so you can heat the thermal store up to 70 or 80 degrees C while you're out of the house, using free energy from your PV. Heat pump manager can control that for you. Okay, obviously, this needs to be designed, as our friend from Kingspan mentioned earlier. This needs to be designed into the product, into the installation from day one. The thermal store has to be correct size, the buffer vessel or whatever you're selecting has to be the correct size, your cylinders have to be the correct size. There's no point in investing in this technology if you have a 200 litre system or even a 90 litre buffer. You're heating 90 litres of water up to 80 degrees Celsius. Okay, that's fantastic. You turn the radiators on, you have loads of heat all over the house, but 90 litres of water will just be gone in no time. You would obviously, put in an 800 litre buffer, a 1000 litre buffer or whatever. If you were going to utilise a system like this, and you'd have some means of isolating that then when your PV wasn't available. But you can do anything. You can engineer anything into a project. The space is always going to be a consideration. Cost is always going to be a consideration. But the technology is there now for the heat pump to look at the solar, to look at the PV, and to integrate with it. And also we can integrate solar tubes. We can integrate solar systems. If there's energy that can be available from solar, we can switch off the heat pump. You can charge your cylinder, you can charge your buffer purely from a solar, and you can use that to heat the house. Okay, and as the solar output drops, then you can switch in your heat pump to boost up the solar. Or vice versa, the solar can back up the heat. All the technology is there. It's all, as our friends earlier said, Scott and our friend, I didn't get the guy's name, sorry, from Kingspan. It just needs to be applied in the correct manner, and it needs to be thought about from day one, and you need to involve all the interested parties all the way through the process. Okay, so that's the end of mine. Thank you very much.
not finished. Just a couple more to go. That heat pump manager is not to scale, by the way. It's not huge. It's pretty small. So taking a look then at running costs and carbon emissions of earth water heat pumps against other forms of heating. These are the current domestic fuels cost comparisons on SEAI's website, and calorific values of oil and gas. And I've taken the air source heat pump, the earth water heat pump, having an SPF 3.8. It's not the best, it's not the worst, I've just taken an average across the board. So when we look at cost per kilowatt for different forms of heating, for every kilowatt of heating using natural gas, we're spending about 7.85 cents. For oil, 11. LPG, about 13. But air source heat pumps, about 4.7. So it's extremely efficient, extremely cost effective. Looking at that then for 10,000 kilowatt hours per annum, again similar cost comparisons. And looking at carbon emissions, grams of CO2. So for every kilowatt of energy we're putting into our heat source, we're emitting for mains gas 225 grams, oil 279, LPG 249, but earth water heat pump around 139. So when we're designing a system, when we're looking at a system from day one, or we're looking at a retrofit, what do we need to look out for? We need to look out that the units are registered on HARP, that the seasonal performance factor is high. You need to look at your ambient conditions and look at a unit that has no or little thermal loss and no ambient conditions, and of course it can heat to the required temperatures. And what air to water can give you is a system that's reliable, that's environmentally friendly. You're utilising free energy from the outside air. You've got low running costs, low carbon emissions. It's proven technology, relatively easy to install, reliable and minimal maintenance. Thank you.